Rolling, folks. Uh, Today we have low pressure dose drain fields with Dr. John Buchanan. John's a registered PE in the state of Tennessee and specializes in design of drip distribution systems of treated effluent. He's a former president of the Tennessee, chapter of the Soil and Water Conservation Society, member of the Tennessee On-Site Wastewater Association. Kind of trip over TE. Whoops, there's not an X after that TE. And he's on the National On-Site Wastewater Recycling Association. When John is not teaching class at the university, that's University of Tennessee, right? He is involved nationally in the advancement of adult education in the on-site wastewater community. I really appreciate what you're doing. Thank you, John, and come on up.
Wow. Look at this crowd. Look at this crowd. This is great, okay? This is fabulous. You know, we had a really great talk in here previously on on-site ethics. This crowd demonstrates the ethics of the Texas group, okay? Because you're here for new information. You're here for continuing education, to meet new friends and such, and I applaud you for that, okay? So that makes the standard pretty high for me. I've got to provide that, okay? And I hope I follow through with that. A question was asked a moment ago. This is a 2-hour session. You got to take a break? Oh, no, we're not going to take a break. I got you to 5 o'clock, all right? And this is a rare opportunity, actually, to be able to get into a topic deep enough, okay, in one of these sessions, okay? The topic is low pressure dose drain fields. So you'll have to pardon me, you know, just as my introducer got kind of tangled up on some of the T's, I get tangled up sometimes with LPP because in 1990s, when I first designed my first one of these, it was an LPP, low pressure pipe, okay? That never really was a good name, but that's what we called it then. And then folks started referring to it as LPD, low pressure dosing system, okay? And then I come to Texas and it's LPDD, low pressure dose drain fields, and I like that the best. I think I'm going to stay with that. As I mentioned, I did my first one of these in 1990, not long after it was first published in North Carolina State, and I really got a full appreciation for giving the whole drain field a drink of effluent, giving the whole drain field a dose, okay? Gosh, let's think about conventional systems. Okay, a conventional system in Tennessee might be a system where we gravity flow water in the first trench, okay? And when that first trench fills up, then some water goes down to the second trench, okay? Well, that might be 10 years from now, all right? Now, 20 years from now, some water might go down in the third trench. And then after 10 years of that, we've got a homeowner that is flat upset with us, okay? Because we failed the field, okay? And I thought, you know, we design all this area. We tell a developer, we tell a homeowner, you gotta have 2,000 square feet for us to put a conventional system in. Oh, by the way, you need some soil too, okay? 2,000 square feet, and then we put all the effluent in the first trench? What's wrong with that picture, okay? We're not spreading it out. And so when I really saw one of these in action, I thought, wow, what can this achieve in terms of minimizing the formation of a biomat, okay? You know, when we pond that water up in a trench, that system goes anaerobic, without oxygen. And the organic matter in the bottom of that trench doesn't have the same opportunity to biodegrade, and so it accumulates. If we can have a trench that gets wetted, dries out, gets wetted, dries out, then maybe we can manage that biomat so that the system will continue to carry water. So fundamental definition of a low pressure dose drain field, a hydraulic network that uniformly distributes primary treated effluent across a treatment media. using low pressure distribution pipe. Okay, for us today, a low pressure dose drain field uses an LPD to deliver that effluent. So here's your classic picture. We've got the source, which may be a home. We've got primary treatment. Still got to have that septic tank. So liquid solid separation. Now, we got a pump in the picture that we didn't have before. So we have a pump tank, and appropriate controls and such, and then the drain field, which is serviced by a low pressure dosing system. Okay, so we've got a layout. My more common application for this is with larger systems. Okay, so schools that are not on sewer, campgrounds like KOA and places like that that are not on sewer. And we build these a little bigger, okay? And we've got to think about different aspects of what we're going to do with those larger systems as opposed to a home-based system. Now, we're all familiar with this technology, okay? We've seen this type of water application method on other media filters. And so you see, oh, I'm really not supposed to say brand names, but there's an Avantex there on top, okay? So we're trickling water down the media, which I like to call hanging towels, okay? And then we have a larger media filter that's home made. The one that you see there is a 40,000 gallon per day system for a subdivision of about 120 homes. But it's using that low pressure dosing system to ensure that water gets spread out over as much media as possible so we can have the biological action that takes place. But for today, our soil is the treatment media. And we want to take full advantage of every grain of soil there is out there to spread that water out and to let those microorganisms do the job. To spread that water out and let phosphorus and other minerals attach to soil particles and have as much renovation of that water as possible. Okay, so that's our goal with this. Now, it just happens to help us often that these can be built on shallower soils. And we'll go through some of those restrictions allowed in Texas, as well as other states that I've been in. But our focus is on why use the low pressure dose distribution or drain field. And then we're going to get into hydraulics, okay? We're going to get our calculators out. You ready? All right. Then we're going to talk about operation and maintenance. This is a technology that got a black eye in the 1990s, okay? We put a bunch of these in the ground in the early 90s, and by the middle 90s, they were failing left and right. And we were having to learn how to maintain them. And they almost went away as a technology. But I think this is a real opportunity. Let me tell you my commitment to this technology. My retirement home is coming up soon, okay? It's coming up quick, and this is a system I'm going to install. I'm going to have plenty of soil. I know where my retirement home is going to be built. I've got soil, okay? I can have a conventional system, forget about it. This is what I'm going to put in, because I can replace a pump, and I can do the maintenance, and I'm pretty sure I can keep this going for a long time in the future. But then look at that picture. Look at that picture, okay? Every one of the trenches is getting water, okay? The grass is greener over the septic system, okay? We're putting nitrogen out there. We're putting phosphorus out there. It's just getting moisture in general. So yeah, we're growing good grass, and every one of those trenches is receiving water. That land that I designated for my drain field is being properly put to use. Okay, so nice little cartoon there. You see the pipe. Those dots are supposed to be orifices, and we got a dose of water coming in. The pump's kicked on, okay, and it fills up the whole length of the trench. One of the things I'm going to talk about a little later on in this talk is the spacing of those orifices, okay? How close or how far apart should they be? Well, with this picture right here, it actually works out pretty good that, wow, if we put too many orifices in there, we could flood that trench. We can put a lot of water in there in a hurry, all right? Now, but if we don't have enough in there, we could have a puddle of water over here and a puddle of water over here, and it would take a while for the moisture to get in between the two of them and defeat our purpose. So we want to get it just right, okay? And we're going to talk about what just right is. So when the pump kicks off, okay, we have this water in the trench. Oh, now there's an interesting word right there, trench. Another T word, matter of fact. I studied your rules, and I studied your rules. And then I studied some rules some more, and I found that the word trench is not in your rules anywhere to be found. The word excavation is, okay? I'm cool with that. That's all right. As long as I finally figured out what you're talking about, but the word excavation. So our excavation has water standing in it now, all right? And so with time, we hope it soaks into the soil before we have the next dose, okay? So what beautiful thing is going to happen there? As that water migrated down into the soil, it pulled atmospheric air down with it. So the gases that we're breathing right now, okay, about 21.5% oxygen, okay, got pulled down into the soil with it to maintain aerobic conditions at that infiltrative surface. The infiltrative surface being right there at the bottom, okay, right there at the bottom, because that's where a lot of the filtering takes place, that's a lot where the biological activity takes place, and much of that needs aerobic conditions to work well, okay? Now, if I can spread that water out, though, and know that I'm getting full opportunity of the soil, then I'm going to be a lot more comfortable putting this on a shallower soil, shallower above a restrictive layer. If I'm putting all my water in the first trench by a conventional system, ooh, I want the full 2 feet, okay, of that vertical separation, because it's going to be a saturated area there. Okay, the other trenches are not receiving water yet, and so with this and having a good, solid, even distribution of water across that area, we can get that water renovated before it gets into that restrictive area. Okay, so using your terminology, the class 4 soils, the good stuff. Okay, we have the good stuff too. We call it 60 MPI soil. It's a little different name for it, just reflects what the old PERT test used to say. And no, we don't do PERT test, but it's a reflection back on that era, okay, that it's difficult soils to get to infiltrate, okay. Well, these can be sited on the class 4 soils, can be sited on a smaller area, okay. So if we've got a small lot or we've got setbacks that are working against us, then we have the opportunity to install a drain field at a homeowner site. Okay, now we have codification in Texas for the low pressure dose drain field. I opened my little blue bag that I got with my registration yesterday, same one you're carrying around, and I found a whole book of rules here. How convenient. I like that. That's a nice, registration gift, because I had to download mine off the web, okay? It was a little less clear. But 285.33D, non-standard disposal systems. Then you go down to D1, low pressure dose drain field. So this is where rules are. And so as I go through this session, I'm going to say, here's what the science says, here's what we do, and by the way, this is what the rules are. And for the most part, they agree. Rules and science don't always get along, okay? But for the most part, they do. And your code describes it as effluent from this type of system shall be pumped under low pressure into a solid wall force main and then into a perforated distribution pipe within the drain field. Okay, that's a good description. But let's go further than that. Let's say it allows to dose and rest your drain field. Okay, it allows distribution that's very, very uniform across your drain field. From an engineering perspective, I have a good feel for conventional systems, which are gravity-based. I have a very good feel for low-pressure dose drain fields. I also have a very good feel for drip. Each of these methods of putting water in the soil have a purpose and a place, okay? I really do think that the place for LPDD in Texas and in Tennessee is much larger than what we currently do, okay? I think it's a great opportunity to get more renovation of the water. I'm going to say a couple things between now and 5 o'clock that are going to go, but my customer won't pay for that. I understand. Trust me, I understand, okay? But I think if we do these things, we improve the value of that piece of property, okay? And we definitely improve the potential of converting wastewater into water. Is that not the ultimate goal of your activities, our activities for being here today, okay? So, must be designed, the planning material developed by a professional engineer or professional sanitarian, okay? Using basic and scientific principles such as the pump must be sized appropriately. I love that, okay? We're going to size a pump appropriately. We're not going to take very long doing it because I suspect most everybody in this room knows how to do that already, okay? Must have pump control system that includes a high water alarm, okay? We're going to do better than that too, okay? So we're going to build a system that will not set an alarm off just because your homeowner had a Super Bowl party. Ever have that happen? Okay? Yeah. All right. So we're going to have enough extra volume in there for that pump tank to absorb that Super Bowl party and give you enough time to get out there to fix that pump before it backs up in their house. Okay? All right. Ah, yes. Let me go back a slide. There it is. The original documentation on a low-pressure distribution system was from this document, Design and Installation of Low-Pressure Pipe. There's the LPP, Waste Treatment Systems, and your rules, the Texas Code, refers to this document, okay? So you can Google it, all right? That's what I had to do, but it's out there. You can find it. I think this is a great time for Texas Extension, maybe Tennessee Extension, to bring this document up to modern code. So I might have to get with Dinesh on that. All right. The one thing I really like about your code, though, and several other states have it this way too, is really breaking your loading rates down to 5 rates, okay? I've got 6 or 7. And it doesn't give me any more additional flexibility. Having 5, I think, is important. But these are gallons per absorpted area per day. Gallons per day per square foot is the terminology I'm going to use. So the loading rates have got to be based on these 2 tables, Table 1 and Table 3 in your code. So we're going to look at the soil and look at your design volume, okay? Your design volume. So what we need is an area, okay? I do engineering talks about topics like this frequently, and I'm quick to say we often need 2 designers together. One of them needs to be a soils person, the other one needs to be more of a technical engineer type, okay? I don't pretend to go out to a site and take a handful of soil and say it's a 3 or a 4. I don't pretend to be able to do that. But once a soils person tells me I've got a 3 or a 4, I'll take it from there, okay? And I'll take responsibility for it for there. But I want that soils person to take responsibility for what type of soil we're dealing with and the depths to the restrictive layers and so on like that, okay? Now, so our first design product is to say how big of an area I've got to place this over, okay? Oh, you've got a wonderful part of your rule here. You can count the side wall, okay, of your excavation. That is marvelous, all right? And so we've got the bottom of the excavation and 1 foot of sidewall as long as we have 1 foot of rock or other trench media in there, okay? So we're going to go down that road. Absorptive area in square feet, our design volume, gallons per day. Application rate, which you saw on the previous table, will give us the size of the bottom or the infiltrative area, okay? Now, in terms of these individual lines, they can be as close together as 3 feet on center, measured center to center. All excavation shall be at least 6 inches wide. I agree with that. I agree with that. The design example we're going to do in a minute is going to be a foot wide because many excavators just don't have a 6-inch bucket. They've got a 1 foot bucket, and that's what they'll use. Okay, that's all that much better. The first one I installed, we installed with a ditch witch. Okay, it may have been 5 inches wide, and we put an 1.25 inch pipe in there, and the gravel on top of that. But that was the original thoughts about how to do these systems. I think it's still working. We'll see someday. All right. I've got to give a little commentary here. So this is where I think the professional that you are sometimes has to kick in over and above the rules. Sometimes I think this. 300 gallons per day for a 3-bedroom home with modern fixtures. That's what's stated in your rules. That concerns me. How close is that to realistic? Do you think it's too high still yet? No, exactly. Thank you. Mine's 450 gallons per day for a 3-bedroom home, okay? And we've always said to ourselves, wow, they're not going to use that much water. But we've been comfortable about that saying, oh, but that's our safety factor, okay? We've been comfortable with that. So this is just commentary on my part, okay? So when you're thinking about 300 gallons a day being very realistic, and that's a realistic number, okay? Mom and dad with young kids, oh yeah. In my household right now, it's me and Ma, okay? Fortunately, Ma's not in the room with us right now, so I can say that. And we got the water bill just a couple of days ago before coming here, and looking at it, we use almost exactly, month to month, 100 gallons of water a day, period, all right? But that wasn't always the case. I digress by saying that's a realistic number. That's a number that people will actually use. And so we may want to up that area a little bit if we can, okay, above the minimum that's required for system design in Texas, okay? All right, so absorptive area for that, 1,500 square feet, includes the excavation bottom, includes a foot of sidewall, okay, on either side of that trench. All right, calculating excavation length. Neat little formula there that's published in the rule. So you have the length, your area that we just calculated a moment ago, the width that you're using, and I'm going to choose 1 foot, all right, and then +2 because we have 1 foot of sidewall on each side of that excavation, and so we divide that area across there to get our length. You know, that equation looked a little intimidating when I first saw it. Okay, it looked a little intimidating because, where'd that W come from? Where did the 2 come from? I want to know where these coefficients come from. But reading into the text a little bit, it's just simply saying we've got a foot of the bottom and then a foot on the 2 sides if we use a foot of gravel or other types of in-trench media. So for this example, the 1 foot width, we need 500 feet of excavation, okay? In my terminology, it would be 500 feet of trench, but 500 feet of excavation, 12 inches wide, that's on contour. We need to get this on contour because if we want a level, even distribution of the effluent, we don't want to dose it in there and have it flow all to the low end, okay? So we need to spread that water out and have it on level, okay? Maintain at least 12 inches of vertical separation above a restrictive layer. So we're supposed to look at the most restrictive soil beneath the system, okay? And whether or not it's rock or fractured rock or other things. But it's different if we have a water table, okay? There is real benefit to using low pressure distribution above a water table, but not necessarily from a choice between conventional and low pressure dose distribution. So either case, we've got to maintain a 24-inch vertical separation above a water table. And believe me, that's good too, because you don't know who's drinking that water next, okay? We all live in the water cycle, but we just don't want our water cycle to be too short, right? Okay? The folks on the International Space Station have a real short water cycle, but they got some pretty high-tech water treatment that's over and above what the soil provides. Okay, now, something I'm interested in though, and you are too, is not just the trench length or excavation length and the distance between the excavations. We also got to take into account how much area this is going to occupy in somebody's yard. We got to draw that box on a piece of paper and say, are we far enough away from a well? Are we far enough away from the property lines? Are we far enough away from the foundation of the house? Are we far enough away from the septic tank? All these setbacks, which can sometimes be difficult to site a system on a lot, okay? So excavations can be as close as 3 feet, measured center to center. All right, I like that. The original documentation for low-pressure pipe systems, the old style, was they had to be 5 feet apart. Well, I was pretty convinced there was a pretty good gap of soil in the middle there that wasn't doing anything for us, but occupying real estate, okay? Having them 3 feet apart feels good. And I can actually justify that with science. That's about right. If they're any closer to that, they'd be overlapping. You'd have a zone of saturation. But about 3 feet's about right, okay? I feel pretty good about that. So we'll use that as our example. So let's say I have to have 5 100-foot excavations and 3 foot on center, okay? There will be 2 feet of non-disturbed soil between excavations, and that means my total yard area is going to be 1,300 square feet, okay? That's not too bad, okay, to be able to site a system, okay? To be able to site a system, 1,300 square feet, not too bad. As a comparison, okay? As a comparison, a conventional system in the same soil and the same daily volume, our minimum excavation width is 18 inches. Our minimum excavation depth is 18 inches, and we'd have to have 3 feet of undisturbed ground in between those excavations, okay? We still need 1,500 square feet of absorption area, but the total area now that would be representative of our drain field becomes just over 1,600 square feet. So it's a bit bigger piece of real estate than what the LPD would require, okay? So I'm just doing that as a comparison, because not everything about an LPDD is all rosy. There's issues, okay? All systems require maintenance, okay? But an LPDD requires you to get out there and actually do something in terms of maintenance. We've got to take some caps off out there. We've got to flush some water. We've got to make sure that our distribution pressure is equalized again, okay? Now we've got a pump out there. Folks will ask all the time, how long does a pump last? And I say, 7 years. And I say that with a smile on my face. 7 years. This is a good number as any, because it may last 7 weeks, and it may last 17 years, okay? But 7's just a nice round number about how long a pump will last. Now, as maintenance providers, we don't want it to last forever, okay? We want to get a little income off of it, but 7 years is about average, and they need to be replaced. Those floats, you know, gosh, those floats. It's fun coming to Texas and visiting your exhibition hall, okay? Because unlike other states I visit, your exhibitors tend to bring in more of the parts that you need as installers and sell them to you give you a discount for coming to the conference. It's wonderful, okay? But up there, there's just boxes and boxes and boxes of floats, okay? They fail, all right? They'll fail before the pump does. And so that's an issue that has to be dealt with low pressure dose distribution. We've got to have electricity out there. Fortunately, your homeowner will never notice it in their bill. We're talking about nickels a month in terms of a fractional horsepower pump running 20 minutes a day. So your homeowner will never know it's there in terms of electrical cost, but we do need somebody to run 2 circuits out there, okay? And this is prescribed in local code and is prescribed in best management practices. We need to have the control system on a separate circuit from the pump, okay? Because the pump is most likely to trip the breaker. And so if we have the separate breaker, then our high water alarm still works, okay? And hopefully the homeowner will notify you. They won't just turn the alarm switch off and go about their business, okay? And we need a Class 2 installer, okay? We need a Class 2 installer. Suspect that most of you are, all right? Okay, so let's say we want one. Let's say we've got a site that fits really good, and from the previous section, we determined the infiltrative area. We needed 1,500 square feet or so. Now we need to design a system that will give an area a uniform dose of effluent, okay? We need to design that system. So one of the first things we want to look at, and this was the fundamental difference about why low pressure pipe or low pressure dosing systems work, is we're going to look at small diameter pipes, okay? We can fill a small diameter pipe quickly. You know, the classical pipe we put in a drain field since 1950, okay, once we got past terracotta, we still dig a terracotta system up every once in a while, but once we got past terracotta, we have the corrugated 4-inch diameter perforated pipe. And it's got a hole that's a 1/2 inch diameter in it, 2 of them as a matter of fact, okay? And so that was the classic pipe. Well, you can think about how much water it would take to fill that diameter up as compared to filling up one that's 1.25 inches in diameter. So we can fill that smaller pipe up very rapidly, and the reason that's important is because we need water at the other end coming out of the emitters so we can get the equal distribution. So we need relatively small holes. That 1/2 inch hole allows all the water that we flush down the toilet to come out the first hole it comes to, okay? My master's major professor was under the impression that if we have a gravel trench, that 4-inch corrugated pipe is not needed, although we still install them and I still recommend them. But the gravel will transmit the water just as well as that pipe will, okay? What we're going to look at, though, is a smaller diameter pipe with very small holes in it, maybe 1/8 inch up to 1/4 inch diameter, so that we can control the rate of water that comes out of it, okay? And you're going to see in a few minutes that I have my preferences. Uh-oh. So typical pressure, 3 to 5 feet of water head. If you're not familiar with the term water head, you're going to leave here an expert, okay? I've got that covered for you. We're talking about such low pressures that PSI doesn't matter, 1 to 2 pounds per square inch. Okay, we can't hardly even measure that with a pressure gauge. So we talk in terms of feet of head for these systems. And the number I want you to remember is 2.31. 2.31, and I'm going to define that even better. A column of water that is 2.31 feet tall will have a pressure of 1 pound per square inch on the bottom surface, okay, just by the weight of water. So I'm going to prove that to you because it helps remember it. 2.31. There's numbers in my life that I have to remember. My wife's birthday, okay, our wedding anniversary, although the year that she forgot it too made me feel pretty good, all right? I have to remember 2.31 as being one of those. I have to remember my phone number. But that 2.31 is right in that mix of important numbers in my life, okay? So the density of water is heavy, 62.4 pounds per cubic foot. So if I have a box that's 12 inches by 12 inches by 12 inches and it's full of water, it weighs 62.4 pounds, okay? 1 square foot is 144 square inches, so 12 times 12. So if I have that cube of water, all right, the bottom of it is going to have 62 pounds of force on it divided by 144 square inches, and that's going to give me 0.43 psi, okay? So where's the 2.31 come from? Well, right there, okay? Here's my cube of water, 12 by 12 by 12. Let's up that. Let's raise that to 2.31 feet, okay? And now I have 2.31 times 62.4 divided by 104 gives me 1 psi, okay? And to get that 1 psi, I have to have 2.31 feet of head. So that's our term, feet of head. Because when we do the low pressure dose system, we're going to put a standpipe out there, and we're going to say, my designer designed this to have 3 feet of head on there. And so when I turn that pump on, I want to watch that water come up that clear acrylic piece of pipe to 3 feet above the surface of the orifices, okay? And I know that I'm running the right rate, okay? So it's based on the height of a column of water. All right, other nomenclature, laterals, okay? I took several days to write this presentation, and I kept using the word pipes, okay, when I really should have been using the word lateral. And so a lateral is a pipe, certainly, that loses water along the length, okay? So we've got orifices in there, or maybe we've got sprinkler heads. Hey, let's go irrigation. Maybe we have a series of sprinkler heads. And so as water travels along the length of it to go out of a water discharging device, the pipe is not carrying as much water. And that's a very interesting hydraulic calculation to make. It makes a big difference on how we do the friction calculations. Now, manifold is still the same thing as a lateral, except it's a lot shorter. A manifold feeds parallel pipes. And that's what we're going to have with our system. We're going to have 4, 5, 6 pipes in parallel connected by a common manifold, okay? So it's the pipe that supplies effluent to the laterals. And then we're going to have a pipe that supplies the effluent to the manifold, okay? Be our supply main line. With an LPD system, we use that pressure to control the flow rate through the orifice. So I said 3 feet ahead, maybe it's up to 5 feet ahead. Well, that hole has so much friction to get water to go through it that it forces equalization across the length of the pipe if we design the pipe correctly. So an orifice is a hole that's precision bored into a lateral, okay? I'm going to talk about it later. We really need a sharp drill bit. I'm going to talk about we really don't need to wallow that hole out. You know, we really need to be precise about doing this. And please don't go all the way through the pipe and drill a hole through the backside too, okay? You really have changed my design then, all right? So if the pressure inside the lateral is greater than the pressure outside of it, water's going to flow through it, okay? And that's kind of silly on my part to put it there, but that is a fundamental definition. So here's our layout, okay? So I've got 6 laterals, okay? I have 1 manifold, and I have a supply main line. You notice at the end of each of the laterals, we have a turn up, okay? I have to always remember when I use the word turn up that somebody asked me one time with my southern accent. Of course, amongst friends here, I have no accent, right? Okay? They thought I was saying turnip, as in the vegetable, okay? I said, no, it's turn up, okay? So we can get a snake in there. And they didn't understand the snake concept either, okay? So, all right. Ouch, an equation. That'll wake you up. We have an equation, we have a model that defines the amount of water that'll come out of an orifice based on the pressure that's driving it, okay? Based on the pressure that's driving it. Now, I could get really persnickety and say this is a fraction of Bernoulli's equation, okay? So I know Dennis got a little kick out of that. I mean, he's an engineer, he feels better. He has seen an equation today, okay? I have pumped him up, all right? Now, part of the world of fluids is based on water, okay? Obviously, water's a fluid. And we think about the pressure, the velocity, the weight of water as it moves through various engineered things. And one of those is an orifice. And so we have the square root of 2gh, and g being gravity, okay, 32.2 feet per second squared. And then h, that's that head, okay? So we're thinking about, do I want to build my system around 3 feet ahead or 5 feet ahead, okay? This is decision time. I can make that decision now, and this is where I'm going to plug it in. So I'm going to introduce you to my favorite orifice scenario right now, because it makes the numbers nice and round. My default LPD, or LPDD, is based on a 5/32 hole and 3 feet ahead. You know why? you get this wonderful flow rate out there called a half a gallon a minute. It's very easy to remember, okay? A half a gallon a minute, 5 seconds diameter hole, 3 feet ahead. So that's where I'm gonna start. I'm gonna put a 3 in there, okay? 32.2 feet per second squared, multiplied by 2, so a lot of us just say 64.4, take the square root of that, and then I've got this area, okay? The area, you see down here about halfway through the slides, or through the words where we've got the formula for it, and we've got d squared over 4 multiplied by pi, okay, 3.14. When you have a 1/8 or 1/4 inch diameter hole, you end up with a very, very small area in terms of square footage, okay, because that's the area that we need. We need that area to be in square feet to make this equation work, okay? So you're going to end up with a number that's 0.0000 something square feet, but don't let that run you off, okay? We've got gravity, we've got our head and feet, and we have this coefficient, okay, this coefficient. In engineering, we have a theoretical model, okay? That's what most of that is, a times the square root of 2gh, and then if it don't work, we add a coefficient, okay? And the coefficient in this case is 0.6, that makes it work. Okay, I'm being a little silly, but not completely. The 0.6 is also based on the thickness of the pipe wall that water's got to go through. And so 0.6 is our go-to coefficient there. So you'll see this written 0.6 times a times the square root of 2gh. All right. Oh, I got to get theoretical for another moment. I'm sorry, okay? Theoretically, that orifice equation is based on drilling a hole into a flat plate, okay? When in reality, we're drilling a hole into a round pipe, and so our hole is actually oval, okay? In terms of the area that is projecting water, it's actually oval, all right? That's okay, it's close enough, okay? Don't get too persnickety on this, it's close enough, all right? And so we don't worry about that. The difference is very insignificant for our application. All right, that 5 seconds. 5 seconds hole bored into a PVC pipe. The pressure is 3 feet of head. Start with the area that needs to be in feet squared. 5 seconds diameter is 0.013 feet in diameter. You worked all that out, 0.00013 feet squared. Okay, is the area of that pipe. Oh, by the way, today is March the 13th. Tomorrow is March the 14th, 3.14. So tomorrow is National Pie Day. 3.14. That's important to folks, okay? That's important, okay? Tomorrow is Pie Day. And I'm going to have mine in terms of chocolate meringue. How about that? All right. Very good. Now, the orifice equation. 0.6 times 0.0013, 2 times 32.2 times 3 feet ahead. Take the square root of all that. I get a flow rate here that looks pretty small, 0.0011, but the units are cubic feet per second, okay? So that's the units we got to play with. Cubic feet per second, we've got an area in feet squared, we've got an h in feet. So we got to maintain consistency among our units. The conversion is very simple. These are numbers I also have committed right up there with my wedding anniversary, 7.481 gallons in a cubic foot, okay? I have a lot of friends that just say it's 7.8, and I said, no. It's 7.481. You got to get it to significant digits. And then 60 seconds in a minute. So we take that 0.0011 multiplied by 7.48, multiplied by 60. Now we have gallons per minute. We've got to get all those units straightened out. And we end up with this wonderful, easy to remember 0.5 gallon per minute, okay? The reason I really like that number is because if I have a lateral that has 20 orifices on it, they're rated for this 5 seconds diameter, 3 feet ahead. I know that pipe needs 10 gallons per minute, okay? 0.5 times 20 is 10 gallons a minute. I can go find a pump pretty quick to do that with, okay? So 3 feet ahead, 5/32 diameter, and same example, half a gallon per minute. If I have a lateral with 18 orifices in it, then I know that I'm going to need a flow of 9 gallons per minute, or I can produce a flow of 9 gallons per minute. If that same system has 5 laterals, then it's just 5 times that to get 45 gallons per minute. So when I turn my system on, I need a pump that can handle 45 gallons per minute against the pressures that I needed to overcome, okay? There's 2 pieces of information I gotta have before I can select a pump, and we just did one of them, and that's flow rate, okay? The second one's pressure, so that's coming up, okay? So many times I get asked a question, what pump do I need? And I have to go through the whole gamut of saying, the pump is the last thing you select. We've got to do the complete system design before we can select a pump, because we've got to know what the flow and the pressure is before we can select that. So, just so that you don't have to go through that calculation again, that I just drug you through, here it is, okay? And oh, by the way, if you leave me a business card or I'm, Texas has this now, I will be glad to let you have this presentation. This is what education is about. Okay, so 3 feet of head down here in the middle. If I have a 1/8 diameter hole, 0.32, 0.5, 0.7, 0.98, 1.28 if I have a quarter. Okay, 1.28 if I have a 1/4 inch diameter hole, that's getting to be a lot of water. Okay, a gallon and a third in a minute as opposed to a half a gallon in a minute. And we're starting to occupy some volume in that trench. So I tend to stay away from these larger flows. I kind of like that low wind. All right, and we're going to talk about that some more too. There we go. All right, orifice spacing. Orifice spacing. My first LPD, LPP, whatever terminology we want to use, the orifice spacing was 60 inches, okay, 5 feet apart. I'm still pretty comfortable with that. So if I have a trench that's 100 foot long, I'm going to drill a hole in it every 5 feet along that pipe. And so I'm depending on that squirt of water coming out of here and that squirt of water coming out of here to occupy this volume in both directions, okay, within a certain period of time that I'm operating that pump. If I go to put too many orifices in there though, I'm going to have an orifice here and an orifice here and an orifice here. They're all going to be squirting at the same time. If I'm not careful, I could fill that trench up with water pretty quick. And the reason that would happen is because our minimum dose volume is based on the volume inside the distribution pipe. So if I have an 1.25 inch pipe here, an 1.25 inch pipe, so on like that, and they're all 90, 100 feet long, I would add that volume up, and I would say the minimum dose volume is equivalent to that. So we need to run the pump for 4 minutes or so. If I've got too many orifices in there, I might fill up my media, and I really don't want to do that. But while thinking about that, just how much storage is out there, okay? Well, if I go 12 inches wide, 100 feet long, and my gravel's 12 inches deep, I have approximately 225 gallons of storage per trench, assuming that gravel has a 30% porosity, okay? That's a lot of water. That's per excavation, okay? My dose may not be that big, okay? Gain 1 for LPD, okay? I've got storage out there. I'm only going to be occupying a fraction of it. And hopefully by the time it comes time for the next dose, that water has soaked into the soil, okay? And so I'm putting water back into an empty trench. Hey, we don't have to use gravel. There's some neat alternative products out there. We could put it inside one of these bundles of packing peanuts. Oh, I wasn't supposed to say that, okay? These expanded styrofoam beads, all right? We could do that, okay? We could put it inside a chamber, okay? So there's other materials we could use out there that we could put the LPD in that occupies that trench. I mean, remember, the sole purpose of that media or chamber or whatever we put in the trench is to hold the trench open. That's the only thing it does. It holds that volume open so that we can store water while it soaks into the soil. Ah, yes, the minimum dose volume. All right, so I said, you know, 5 times the volume of my distribution pipes. 5 times the volumes. Now, that was not, and I repeat, that was not written on the 3rd tablet that Moses dropped on the way off the mountain, okay? That's a number we came up with in modern times. You know, about 5 times sounds good. It's not as big as 6 and it's bigger than 3, okay? So we say 5 times, okay? Well, it's become written in rule. I mean, it's written in the rules that we follow in terms of how to design one of these systems. So 5 times, okay? The goal is this. When that pump first kicks on, that first orifice is squirting water, okay? Within seconds of that pump kicking on, that first orifice is squirting water. It may take a couple more seconds before it gets down to the other end of the pipe, and this last orifice starts squirting water, okay? So that means every time that system kicks on, the first part of the pipe is going to be producing more water than the last part, okay? So what we do, we say the system needs to run long enough at steady state such that this is such a small percentage of the total volume that it's insignificant, okay? Okay, this gets 0.1% more water than it did down here. Who cares, okay? So that's our goal, to run it long enough to where we don't care if it gets a little extra water. So we've said 5 times the volume, all right? Well, we look at that. And let's say I have 500 feet of 1.25" diameter PVC pipe scheduled for you, by the way, okay? That volume is 39 gallons. So therefore, my minimum dose is 5 times 39, 194, and at 45 gallons per minute, I need to run the system for about 4 minutes to produce that volume, okay? So my minimum dose becomes about 4 minutes. With the close orifice spacing, if I have too many of those orifices in there, in that 4-minute period, I could put too much water out there. So the balance is the size of the orifice. The smaller it is, the least amount of water it's going to produce. It's a balance of the pressure. The less amount of pressure I have, the less amount of water it's going to put out. And the number of orifices along the line to balance out the distribution and the volume of the water, okay? So, you know, more orifices is going to result in a greater flow rate per lateral. That means a larger diameter pipe. Bigger pump, may not be too significant a cost, may flood the trench, so it's better to have a lower pumping rate and smaller diameter laterals, okay? Let more of the water soak in the soil between doses. Now, there is a minimum, okay? I believe in drip, okay? I believe in drip irrigation. But the size of those orifices are on the microscopic scale, okay? Because there's this long tortuous path that water has to flow through, okay? So it's a little bit different than just orifice. But with that technology, we have to be very concerned about solids. So one of the first things we do with a drip system is put a great set of filters in place. With LPDD, we don't necessarily put filters in place. So we don't want those holes to be too small. We want them to be reasonable size to control the flow of water, but yet be able to pass some of the material that's going to grow inside that pipe and be transferred inside that pipe by the pump. Okay, so it's a balance. This is a mistake on my part. I built this as part of my training center in Tennessee, and it looks like a wonderful squirting fountain, okay? All right, and you know, my whole point was to demonstrate that we can make those squirt heights all be the same, even though they were on different elevations. But I drilled them too close together, and the amount of water that came out of there just, you know, that flooded that ground in just no time at all, okay? So how are we going to determine the diameter lateral now, okay? I made a big deal a few minutes ago about, a lateral is unique. It loses water along the way. Well, that's kind of going to mess up my equations that I have to measure friction with. So the flow from each orifice needs to be uniform. The problem is, due to pipe friction though, I'll have different pressures available to squeeze water out of there along the length of the pipe. I'm going to lose pressure along the length. So consequence, if the pressure changes, the orifice flow changes along the length of the pipe. So I need to select a pipe diameter, okay, that won't let this happen. So my water's coming in here on the left side. My water's coming in here. Did I say left side? Yeah, that's the left side, all right. And I'm losing friction as I go, and you can see that the height of the water coming out of it varies along the length, and that's not desirable. That's not what we want to do. And so what we want is this. We want the amount of water coming out of those holes to be the same, close, as we go along the length. But look what's happened hydraulically. For this particular example, I've got 4 gallons per minute coming in. Well, I lose a half a gallon per minute there, so I now have 3.5. I lose a half a gallon a minute there, now I've got 3. On and on and on, till this last section only has a half a gallon a minute going through it, okay? That's a unique set of hydraulics. We're losing water along the way. Here's a rule of thumb. Here's a rule of thumb. Rule of thumb is that we want the pressure it takes to force the water up through that orifice to be 10 times greater than the friction pressure loss it's going to have going across it, okay? Now, I didn't make that up. We use that in a lot of lateral situations. We use it in irrigation. We use it in wastewater treatment plants. So it's a well-established engineering corollary, if you would, okay? But ultimately, our goal is to limit the variation among orifices to plus or minus 10%. So one to the other, plus or minus 10%. So if I'm using 3 feet ahead as my design orifice driver, then the friction in my pipe needs to be somewhere in the neighborhood of 0.3 feet. 0.3 feet of friction. Turns out that's pretty doable, okay? So calculating friction in a lateral, we can use any of the traditional friction loss equations. Hayes and Williams is the most common, okay? When you pick up a pipe table, and I'm going to show you one here in a minute, most likely it was done by Hayes and Williams, okay? And so the way we'd go about it is this. We'd break that pipe up into sections between the laterals. I'm sorry, I said that wrong. We'd break it up into sections between the orifices. So if I come in my pipe, begin in my pipe, and I have an orifice at 2 feet or 5 feet, that's my first section. Section number 2 is 5 feet in between the first and second. Section number 3 is the orifice, is the gap between the pipe between the second and the third. So I add all those up. So my first 5-foot section is going to have 9 gallons per minute. I do my Hayes and Williams equation, or I'll go to my pipe table, and find out I have 0.23 feet of head loss. Second section has 8.5 gallons per minute, 0.2 feet of head loss. Second and third, all the way down to I get almost none down here at the far end because I've only got a half a gallon a minute going through 1.25 inch or 1 inch pipe in this case, okay? So I add all this up. This looks onerous. That's why we had tables, okay? All right, but this is what I got out of it. Here's my 18 sections. I had 18 orifices in that pipe, okay? I get my greatest friction at the front end because I got 9 gallons a minute squeezing through there. Then I have 8.5, and then I have 8 and 7.5 and 7 going down through there. And I add all that up, my friction in feet, turns out that I have 1.55 feet of friction loss in that lateral, okay? 1.55 feet of friction. So what that means to me from an orifice standpoint, I went from 3 feet of pressure, 3 feet ahead, to drive that 0.5. That really should be 0.5, but I'm a persnickety person, so I got 0.49 there. That's really 0.5. What that means is now at the distal end, I have 1.55 less head pressure. And so the flow rate out of that distal one's going to be 0.34. okay? It's going to be 0.34. My variation is much greater than 10%, okay? So this is what it really looks like. All right, that was 1-inch pipe. 1-inch pipe is too small. Let's go to 1.25 inches. An 1.25 inches is kind of where I like to start anyway. I did the same exercise. My first orifice will flow at 0.49. My last orifice will flow at 0.46. Okay, 0.49, 0.46. My variation betwixt those two is within 10%. I'm good. Okay, so I know I've got a pipe that'll work. And so this is what it looks like. Yep, this is producing a little more water than it is down there. All right, but it's within 10%. I'm okay. I'm happy about that. But I'm a persnickety sort. Let's do an 1.5 inch pipe. You know, I got time on my hands, right? And so the difference between the 1.25 inches and 1.5 inches, my first orifice is flowing at 0.49, the last one's 0.47. That's pretty outstanding, but that's overkill, okay? It's wonderfully flat. You can see that it's, you know, we still got a little more flow there than we do there, but it's overkill, okay? And we don't really need to do much better than that. So we can ask the question. We can ask the question. 1.5 inches is definitely a little better than 1.25 inches, okay, for the 90 foot. If it was 60 foot, it would probably be a no-brainer. But 100 foot kind of gets that point of getting kind of close, okay, to being a call between 1.25 inches and 1.5 inches. If I'm going 150 feet, it's going to be 1.5 inches. If I'm going 200 feet, it's probably going to be 2 inch, okay? So it's going to depend on how far I'm pushing water. Considerations, you know, the 1.5 inches is going to be more expensive. But hey, with that expense, I've got a thicker wall. With a thicker wall on that pipe, I've got some durability. That's something to consider, all right? Other considerations. Maintenance. I can maintain the 1.25 inch pipe, but I can maintain the 1.5 inch pipe a little easier because I've got more room to work with a jetter or a pipe snake or something like that. But then I got the flip side. Okay? My minimum dose volume with the 1.5 inch is going to be bigger because the 1.5 inch diameter pipe holds more volume. And so my minimum dose volume is going to be larger than it is with the 1.25 inches. And if I'm using an LPD in Texas and in Tennessee, I'm probably already on a limited soil site, okay? I'm probably thinking about LPD because I've either got a setback limitation or depth of soil limitation, and therefore I really want to not flood the site. So the smaller diameter pipe that the smallest diameter pipe that provides the uniformity that I need is my best choice from a limited site, okay? Because I can put the minimum amount of water out there per dose. Okay, if you have experience doing irrigation laterals, I've used the irrigation word several times. We're kind of in that business. We are watering the ground in this case, all right? But if you have some experience doing irrigation, there is a lateral design formula or methodology called the Christensen friction factor that actually makes this process that I just went through very simple, okay? So instead of doing all these sections, 18 sections and 18 additions, the Christensen coefficient would look at that one pipe and divide the friction by another coefficient depending on how many orifices you have. But there are, and I throw that out to you from standpoint if you've heard of this methodology and it's perfectly legitimate for this task. Otherwise, it's a little more complicated than what I want to spend 2 hours doing today. All right. You made it through the first hour. Good job, okay? Good job. We got another one to go. A better layout, okay? Earlier I showed you a layout that had all these pipes connected at the end and one supply line coming in. This is better, okay? One of my concerns with LPDD is that if we just have that one manifold connecting all the pipes at the end and we have it on a little bit of slope, then when we turn the pump off, the water can flow from the higher lateral down to the lower lateral. It's called gravity, okay? It will flow to the lower lateral. So the lower lateral may receive more water than what we really intended to it, okay? And we can have a breakout down there. In my world, that's called a failure. Does it work in your world too? If you have a breakout of effluent on the soil surface, do they use the F word and not the four-letter one? Okay, it's a failure, okay? So we want to minimize the issue of failure, okay? Notice on this that the manifold is small. It's up there at the high end, and the water has to, if it wanted to move from this lateral down to this lateral, it'd have to backflow up and come back down to get here, okay? This is a better design. I really encourage this. So the goal is to isolate the laterals from each other hydraulically, okay? So water cannot drain from an upper lateral down to the lower lateral, okay? This is a better design, and this is where we want to go in terms of building these systems, okay? So one of the last systems I did, I pulled my AutoCAD drawings up and cut and paste them a little bit. And you know, these kinds of things really help do the maintenance. Unions cost money. Unions cost money, but they sure make it simpler to work on in the future, okay? My standard saying is build it as if you're going to be the service provider for the rest of your career. Make your life easier, okay? It's sometimes tough to get the homeowner to buy into it, but you know, think about that. You know, and we're gonna laugh at me a couple times yet today, okay? Here's one of the big ones that we're gonna laugh about. I've got written right there, ball valves. Nah, not anymore, okay? Gate valves is the way we're gonna go with my designs. It's lessons learned, okay? Ball valves stick, okay? They stick. I don't know what the deal is with them. And then when you try to do that micro adjustment on them, it's just so insensitive. So I try to get customers to buy gate valves rather than ball valves. All right, so a couple issues we've got to deal with. All right, we've got an elevation here of 476. I tried to find a good elevation for Texas. We've got an elevation here of 471, okay? Understand in my part of the world, these would be in the thousands. So these are at two different elevations. That means we have two different pressures on them just because of gravity. You notice, okay, hopefully you might be able to notice, oops, did I go? Yeah, there it is, that the squirt height's higher on the lower one than it is on the upper one because of that elevation change. So what we need is to add these valves, not necessarily right there, but that's just for kicks and grins right now, that we can squeeze this down a little bit. We can put a little extra resistance on that system by squeezing that valve down till we get an equal squirt height, if you would, between these two laterals. Now, I don't want those valves there, okay? I want those valves there, up here. That's going to do the same thing. Me and this clicker are not getting along. All right, come on, one more, there you go. I want them up here, okay? So that's part of what these valves are going to do. Now, I could also have laterals that are not exactly the same length, okay? I can get away with that if I've got those valves to control the pressure. A shorter lateral, okay, is not going to have as much friction on it. So I can add the extra friction by closing that valve down on that particular line, okay? So again, the manifolds for equal distribution, accounting for elevation change, accounting for length of pipe, accounting for flow and such. Okay. So again, lesson learned, there's all kinds of valves out there. The globe valve would probably be the most sensitive. Okay, you can just turn that a little bit and see a difference in flow, but it's got a lot of places there to collect solids. That's a little concerning. The gate valve's a nice in between. It can be maintained. You know, I do a lot of threaded fittings. I try to minimize how much glue fittings I have, and I've got the great big X to the ball valves. I'm not saying don't use them. I'm just saying if you got an alternative, if you can get your customer to pay for it, go with these. Now, I also have to say this. Don't go with PVC gate valves. They'll break off in your hand, okay? And you know that already. All right. So yes, I have used ball valves for flow control. This is one of mine. So you can see my manifold, my supplies coming out to my individual laterals. Here's the inside the box, okay? Also, as a side note, I'm good with the pressure-treated wood being the sides of the box, but I wasn't good with my property owner using plywood for the top. That didn't work too good at all. All right, manifold and mainline design. So we've got to make another decision. We've got to decide what size pipe to make our main line out of. For this example, I upsized you a little bit. I've got 18, I've got 9, and I've got 6 pipes in this example. So I'm upsizing up to 54 gallon per minute. Okay, I've got to make a decision. What size pipe am I going to run from the pump to my manifold? And further, what size manifold do I need to handle 54 gallon per minute? The way an engineer looks at this is, what's the velocity inside the pipe at that flow rate, okay? And so we have a generalized notion that 2 feet per second is too slow, and 5 feet per second is too fast. We have that notion. The notion is that if I've got pipe that flow in at 2 feet per second, it's too big, okay? But if I got a pipe that's pumping more than 5 feet per second, it's too small, okay? I've got more friction. It's that design point where the friction really starts to eat up electricity in a pump, okay? So I try to keep it between 2 and 5, all right? At 54 gallon per minute inside a 2-inch pipe, I get 5.2 feet per second. That's good enough. I mean, that's okay. We're not pumping miles and miles and miles. We're pumping 100 feet, maybe, okay? That's really okay. 2.5, the velocity would be 3.6 feet per second. That'd be okay too. It's greater than 2, okay? You know, there was this third tablet that Moses dropped off the side of the mountain, okay? And on that tablet, it said, thou will always maintain 2 feet per second of flow inside a pipe. That truly was on that document, okay? And we do hold that dear. So it needs to be greater than 2 feet per second. Now, just to really impress you, just to really thrill you, and to make Dennis happy again, here's another equation, okay? Here's how we do it, Q equals VA, okay? If there's one equation that a hydraulic person that feels dear about, is flow rate equals velocity times cross-sectional area. And there it is. But I got a better way of doing it. And it's the way I do it on a daily basis. It's called a pipe table, okay? Here again, if you'd like to have my copy of my pipe tables, I'd be glad to send them to you because I have this in a spreadsheet, okay? And so notice here we have Schedule 40, IPS. What does IPS stand for? Good job, guys. Iron pipe standard. A long time before there was PVC pipe, there was steel pipe. And it was Schedule 40 steel pipe, Schedule 80 steel pipe, Schedule 120, just like we talk about plastic. So it's an iron pipe standard. And so for us, it's PVC that guarantees the threads work the way we want to. It makes sure that the outer diameters work the way we want to, so we have the proper connections and everything. Oh, I got to do this to you. What's the difference between Schedule 40 and Schedule 80? Wall thickness, but in which direction? Exactly. Smaller internal diameter, same outer diameter. So your glue-on connections still work, okay? So from a Schedule 40, Schedule 80 nomenclature, the Schedule 80 is going to have less flow than the Schedule 40, okay? So here's my Schedule 40, 1/2 inch, 3/4 inch, 1 inch, okay? On and on and on. Here's my flow down this chart in gallons per minute, and this one's so nice. This chart, I've got it color-coded in green to where it says, nah, velocity's too high, okay? So we can go through there. This gives us our internal diameter, our outer diameter, wall thickness, all this information I put in for my benefit too, so we can do this. So From this one piece of information, we can get the diameters, the flow rates, and the friction loss, in this case, PSI per 100 feet, without having to do all those calculations. And that's the important message down there. All this information without getting the calculator out. Okay, so we could go with 2, we could go 2.5. We could go either way and feel comfortable about it. Which is going to be less expensive? The 2 or the 2.5?
2.
The 2, certainly, the 2. All right. Another interesting price break is when you migrate over to 3-inch diameter, okay? There's not a heck of a lot of difference in cost between 1.5, 2 and 2.5-inch fittings. But when you start buying 3-inch fittings and 4-inch fittings, the price goes zip, and you know, and their Home Depot, Lowe's 84 Lumber is really glad to charge it to you, okay? I mentioned 3 brand names there I probably shouldn't have had, okay? Do you think the salespeople at Home Depot, Lowe's 84 Lumber know the difference between DWV and PW? Agreed, they don't, okay? So again, we're building a pressure system. We've got to use the PW fittings that has a full inch, 1.25 of glue surface to glue stuff to. Okay, good stuff. Very good stuff. Oh, we're good. We're all good on time. All right, Texas says, if you're going to build an LPDD, we have to have a control panel, okay? And we have to have an alarm. We can keep our control panel simple, but I kind of like to make them just a little bit more fun, okay? We've got to have a pump tank, okay? That's going to be different than just a conventional system. And of course, we've got to have flow. So we've got some decisions to make. Okay? Here's where I'm going to cost you a little more money. Okay, and it's a decision you can make. Okay, Texas rule for pump tank sizing shall contain 1/3 of a day's flow between the high water float and the inlet to the pump tank. 1/3 of a day. Buchanan's rule, a full day. Okay, that costs more money, but I've got to stick with that. Okay, I've got to stick with that. That's what separates the pump tanks from sending the alarm off during a Super Bowl party. Okay, and we really don't want the homeowners doing that. 1/3 of a day is not a lot of volume when your volume that you're using for your design flow is already realistic. Okay, at 450 gallons per day for me, I've got wiggle room. At 300 gallons per day for you guys, you don't have much wiggle room, okay? So, I have the luxury, I have the honor of being in front of you. I have the honor of being in front of you. I have the honor of being in front of other folks and talking about septic systems. I mean, but as much as I say to folks, you got to spread your laundry water out, wash a load of clothes that day, wash a load of clothes that day, and wash a load of clothes that day. My wife and I are the 2 biggest hypocrites. Come Saturday, we're going to wash the whole house of clothes, okay? And so what's that doing to the drain field? In our household, we only use 100 gallons a day on average, so it's probably just waking ours up a little bit. If you've already got a house full of people, and you got an LPD, D, you wash a load of clothes, and you've only got 1/3 of a day's flow, you're going to set the alarm off on Saturday, okay? So I really think this needs to be a bigger number. So Buchanan's rule for pump tank sizing shall contain a full day's flow between the high water alarm float and the inlet to the pump tank, okay? Pump tanks and floats. You truly haven't been a member of this industry, okay? There is a fraternity within our industry that has floated a tank at some point in time, okay? I am a member of the industry, okay? I have floated a tank. I was embarrassed, okay? But it happens, okay? But pump tanks are especially susceptible to floating a tank because it doesn't maintain a water line like a septic tank does. Septic tank, you have an outlet elevation, and that's where the water stays, unless it's leaking. But with the pump tank, you're pumping it down, and water comes back up. You pump it down, and water comes back up. So a design factor with low pressure dose drain fields is to take into account the buoyancy of the tank. Okay, we've got to take that into account. So on my first cut of this, I'm going to think, okay, I'm going to have 300 gallons that I'm going to be dosing. Okay, so that's active, that's going up and down. I'm going to have 300 gallons above the alarm float to the inlet. Okay, but then I've also got to have on the bottom enough volume of water, enough weight of water to counterbalance buoyancy in addition to the weight of the tank. And oh, by the way, if I can keep the pump motor underwater the whole time, that's a bonus, okay? If you have the traditional green pump, maybe I shouldn't have said it that way, they've got all colors of them up there, okay? But if you have that traditional pump where the motor's on top, we really do want to keep it submerged. There is the cooling issue, okay? There is keeping it cool. The pumps are better than that. They really can handle that. To me, what's more important is having it exposed to that atmosphere inside the tank is extraordinarily corrosive, okay? If you could survive below the water level, you'd want to be below the water level in a septic tank or a pump tank, okay? The atmosphere is much more corrosive to metal than the beneath the water level is, okay? So in thinking about, point it this way. There you go. If you think about how to do the calculations and such, almost lost my point, almost lost my train of thought. There it is. I have a supplier, okay, for my 1,000-gallon tank that I'm going to use, that I might use. And by that supplier's design, the tank weighs 8,000 pounds, okay? Now, but the issue is for us is the volume that tank displaces, okay? So that tank is 12 feet long. It's 5.5 feet wide. It's 5.8 feet tall, okay? Multiply those three numbers together, you get 179 cubic feet, all right? The equivalent weight of water then is 11,000 pounds, okay? So if my 8,000 pound tank is in this volume surrounded by water, so I have a high water table, I have soupy soils, whatever, its weight of 8,000 pounds is less than that weight, and therefore it will rise, okay? Oh, and it's not a pretty sight either, okay? So what we have to do is add extra ballast to it. Now, that foot of soil we're going to put on top of will probably take care of it by itself. The resistance that that tank wall is going to have coming up through the soil may hold it in place. That's safety factor, okay? I want to balance that difference. I need 3,200 more pounds, 3,170. I need 3,200 more pounds to get up to that 170. And so if I divide that by the number of pounds a gallon is, and it's 8.34 pounds per gallon, I need to keep 380 gallons in that tank to maintain that ballast, okay? So that's my thought process. So I've got about 400 gallons there. I have about 300 gallons of dose volume, about 300 gallons of alarm volume, okay? So as shown here. Now I've got a place to put my floats, okay? Now I know about where I'm going to keep my floats. I want to keep that pump submerged, okay? So that's my minimum volume, which also includes the ballast to hold the tank in place in case it gets pumped down. And then here's my volume that's going to go up and down with my dosing, okay? And then here's my alarm. And it's well below the inlet to the tank, so I don't have water backing up into the homeowner's house yet, okay? All right. Now, a point. Remember, we're still dealing with septic tank effluent. We're not dealing with secondary quality water. We're dealing with septic tank effluent that's still going to grow biological solids in there. You're going to transfer some solids in from the septic tank every now and again. So we've got to remember to have the pump off the bottom of the tank. I have put many concrete blocks out there and put the pump on there. Okay, I've done that. I've matured. Okay, I want to recommend a pump vault, which you see here, okay? It's a cost. That concrete block was cheap, okay? Probably had one in the back of the truck already. It was very inexpensive. But if we can come up with a material, and these are available, that can provide extra duty, I'm kind of excited about it. This is going to provide some filtering, okay? If it filters, that means we got to clean it, okay? That's good and bad. But it's going to, minimize how much stuff, and stuff's a more polite S word in our industry, that's going to go out into the field. They didn't catch that one, did they? Right over there. All right, now. All right, so this is a place that we can hang the the pump from, and then we can have separate float trees in there, okay? So most folks agree. We had a really good talk on ethics a little while ago, very good talk, okay? Most of us agree it's not the best method to attach your floats to the standpipe of the pump, okay? It's not necessarily wrong. It's not necessarily right. It's just most of us have agreed on that concept that we'll use a float tree rather than standpipe, okay? That way, when we got to pull that pump out, we don't upset the location of our floats, okay? So that's a best management practice, if you would. And of course, we've got to have that union up there at the top, okay? We've got to have that union so that we can disconnect a pipe without having to cut it and pull it. Secondly, we got to have a good rope, okay? We've got to have a good rope attached to that pump that we can pull it up with. We don't want to pull it up by the extension cord, okay? We don't want to pull it up and we don't want to necessarily have to pull it up by the pipe. We may break that pipe just by the weight of the pump. So we've got to have a good rope up there. And then the last thing I want to say about this scenario is when you order your pump and when you order your floats, make sure you order sufficient cable on those that you can pull the whole shooting match out and set it off over to the side without having to cut any cables, okay? So make sure you order sufficient cable to go with all that. All right, selecting a pump to go in an LPDD, all right, selecting that pump. Selecting a pump is about the next to the last thing we're going to do because we've got all these other things to take care of first. We've got to figure out, what kind of pump we're going to have, what kind of flow we're going to need. Well, we've already got that. And how much pressure we've got to accomplish to get to the LPDD, okay? So remember how flow rate's determined. In this example right here, we've got 4 laterals, 1, 2, 3, 4, 16 orifices per lateral, going out like that, half gallon per minute per orifice, so 8 gallon per minute per lateral going across there, multiply that by 4, we have 32 gallon per minute, okay? Now, we've got to know about where our high water level needs to be and our low water level needs to be. So we need to know about our tank. We need to know if our tank, I'm sorry, I said that wrong. We need to determine the gallons per inch of our tank, okay? So we have an area. We have a width and we have a length, okay? That's an area. So if I come up 1 foot of that area, well, that's 1 foot times the width and times the length, and that gives me cubic feet for 1 foot depth. 1 cubic feet is 7.481 gallons of water. Now I have gallons per foot, okay? I can divide that by 12 and get gallons per inch that way, okay? So I know I got to have 400 gallons at the bottom, so I can take how many gallons per inch that is and figure out what that low water level is. I know I've got 300 gallons a day that I'm going to be dosing back and forth, okay? So I can figure out what this level is. I can figure out what my minimum dose volume is, okay? Remember, I have to do 5 volumes of the distribution pipe. So that might be up here, and so that would be a level that suggests to the control panel, this is your minimum depth, okay? All right, so pump curve. My goodness, what happened on the side there? All right. That's what happens when we put a PC-derived thing in somebody's Apple computer, all right? All right, so on this axis is supposed to be pressure, okay, in feet of head. On the bottom axis is supposed to be flow rate in gallons per minute. So pumps, especially centrifugal pumps, have this shape, okay? So go upstairs in a little while, here in a few minutes, not right now, but here in a few minutes, and ask that supplier for the pump curve and press them, okay? So I want to see what your pump can do at various pressures and what the flow rate's going to be, all right? Now, right now, we know what our flow rate is because we've added up the number of orifices, we've added up the number of laterals. So we know what this is. So we want to be able to come up here with that particular pump and see what kind of pressure it can generate, okay? And see if that pump's going to work. But before we can do that, we've got to figure out how much pressure we need, okay? And there's two ways we go about it. We look at the static head and the friction head. All right, now I mentioned that tank a few moments ago. We got to figure out what the low water level is, okay? That's the lowest that I'm going to be pumping water from. I've got to figure out where my elevation is to my dose drain field, okay? So is it 3 feet of elevation change? Is it a Tennessee system we might have 50 feet of elevation change? Okay. Am I pumping it around to the front yard? All right. So that static head is what we call part of that is called the elevation change. The second part of it, okay, well, there's elevation change. Second part of it is the pressure required to operate the orifice. So if I've got a 3-foot pressure head requirement for my orifice, I've got to add 3 feet to that elevation change, okay, to get my static head. So that's the total elevation change and pressure requirement that I need at the distal end. Now, I'm going to add in the friction part. And if you remember that pipe table a few minutes ago, it had what the friction in PSI, so we got to make that unit conversion, is per 100 foot of length for a given flow rate and for a given pipe diameter. So it did the calculation for us. So it's relative to the roughness of the material. PVC is very smooth, okay? PVC is very smooth, so its friction factor is actually very, very low, but we need to know what it is. It could also be a function of filters. There are some LPD systems out there that do pump water through a filter first, okay, to help give the lateral some longevity, okay? And of course, the higher the flow, the greater the friction. So those are concepts we've got to take into account. So when we think about the dynamic head, okay, the total dynamic head, it's a combination of the static head and the friction. And ultimately, this combination is the pressure that the pump can produce at the flow rate we need, okay? So if we need 45 gallons per minute, and we have 5 feet of friction head, and we have 10 feet of elevation change, and another 5 feet of pressure requirements, then I need that 45 gallons per minute against a 20-foot head. Okay, those are nice round numbers, easy to add up in my head. I hope I got it right. Okay, so we have 2 points to pick a pump. Okay, so those 2 points now are going to intercept my system curve somewhere. Okay, so this is from my pump manufacturer. This is from the pump manufacturer right here. This is from my system. Okay, now as you see these 2 numbers, it looks like they intersect over 20 gallons per minute. Okay, they intersected over 20 gallons per minute, and then you can back trace that line back to about 48 feet ahead, about 48 feet ahead there. If that works for us, then we just found a pump. Okay, and that's a pretty cool system, cool way to do it. Now, one thing that we don't often say is, in fact, we have a range of flows in an LPDD. We're going to start at the low water, we're going to start that pump when it's at the high water level, okay, or a higher water level, and then it's going to pump down. So we're going to start it down here where it has a little less static head because we've got a higher tank, and then it's going to work its way back a little bit because when it gets down to the low water level, it's got to work a little harder, okay? So that's why the low water levels are the design point. At the high water level, or whatever higher level we're using to start the pump with, the pump does not have to work as hard. It has to work harder as it goes down because it loses, or I should say gains, elevation head. So that's why we really have a range when we kick that pump on. So, decision time. We got another design element to do. Do you want a demand dose system or do you want a timed system? Okay? Your rules don't specify that. And I think that's okay. That gives you flexibility. If I'm on a limited soil, if I'm trying to protect a site and only have a foot of soil to work with, I'm going to go with a timed system. Okay? If I've got plenty of soil and my other resources are okay, then I can go with demand. I'm going to put a bigger dose of water out there per dose, but my control panel just got $100 cheaper. Okay? So that's worth something. That's worth something right there. So a demand dose system is a little cheaper, but not necessarily as environmentally sensitive. Oh, that sounded persnickety, didn't it? Okay, environmentally sensitive. It's not as gentle on the environment in terms of getting water renovated as the time dose system is. With the time dose system, we're going to put out spits. We're going to spoon feed that soil. Okay? With the demand dose system, as you see here, when that water level gets up to here, we're going to kick that pump on, and it's going to pump till it gets down to here. Okay? So we've got that full dose volume that we're going to put out there. If my soil can handle that, that's the least expensive way to go. Okay? Now, Buchanan says a piggyback switch is not a control panel. Okay? I have a personal beef against piggyback switches. Okay? I put down here in small type, down here at the bottom, a piggyback switch is okay for a basement sump pump, but not for a septic system. And I really don't like them in basement sump pumps either. But, so you've got a device here that's easy. They're easy. You put a float cable in there and you plug it in, and then you plug the pump into the back of the piggyback switch. So when the switch is in its closed position, the pump gets power. And when it drops down, the switch opens and it cuts off the power to the pump. Man, that's simple. Okay? It's wonderfully simple, but there's too many folks that do it just like this. They put an electrical receptacle out there in that environment, and they just plug it in, and it's going, nah, no, we need to upgrade to a panel. Now, fortunately here in Texas, they kind of keep you from doing it anyway, because you got to have an alarm float, okay? So you're at least going to have that level of control. Really need to upgrade to control panel. All right, with time dosing, we're going to have the same kind of floats that you see, and this is one variation, but with time dosing, our next to the lowest float is going to be one that comes up and says, we've got enough water in the tank to do a minimum dose, okay? So if my minimum dose volume was that 200 gallons, then I'm going to set that float such that I have at least 200 gallons between it and the off switch, okay? Now, if it comes up above that, that's okay for the time being. But at least says I've got at least enough volume in my tank to do a minimum dose. So we're going to call that the enable float, okay? Depending on the manufacturer of that control panel, there's a couple of different ways these enable floats work. Sometimes the enable float will, if it's down, will cut the power to the timer, period. And the timer will not advance, all right? Others, the enable float will allow the timer to advance, but it won't let the pump start until it's up, okay? And if you're a service provider, sometimes we have to do something really onerous and get the owner's manual out, okay? Read the directions, okay? But we've got to make sure that we're within that. Okay. What's the elevation change between a low water level and the drain field? I'm asking this from a Texas perspective, okay? Because Texas says you need an anti-siphon device, and so does John, okay? You need an anti-siphon device. If you're pumping up a standpipe, going up and then down to a lower drain field, you've just created a siphon, okay? And so the, the traditional method was to drill a hole in the standpipe. A little hole, but that's the traditional method, okay? I've done that too, all right? Now, Texas also says if you're pumping up to a drain field, you need a check valve, okay? I'm okay with that, but Texas is a lot like Tennessee. Every once in a while it gets cold here and stuff like that creeps up on us, okay? So if you're gonna put a check valve in a line, that main line is gonna be full of water all the time, okay? And so if you have a cold snap and you're not necessarily below the frost line or something like that, you can freeze the pipe, okay? It happens every once in a while. So that's just something to take into account by Texas rule, but make sure it will not freeze, okay? So instead of drilling the hole, okay, I'm gonna up the game a little bit and say, put a T up here at the top. And when you come out this way, maybe bushing down to a smaller pipe with a small valve on it and let that be your opening. So water is actually coming out during the pump. You know what the flow rate is. And then when the pump stops and it has the need to suck air, the air can come up through here, okay? And so the advantage of this is once you drill that hole in that pipe, it's kind of hard to go back on it, okay? Without replacing the standpipe. So that's kind of hard to fix. If we have this, we can create our own very controlled leak, okay? All right, installation. You can't see it in the slide very well, but we laid out hundreds of little red flags for my outstanding backhoe operator to follow, okay? This backhoe operator, I mean, all you guys who operate backhoes fascinate me with that smooth running. It fascinates me to watch you guys. I'm so jealous. All right, we need to construct the laterals. So here's my 1.25" PVC pipe. I want to specify bell and socket. Okay, I don't want to put a bunch of couplings in there. I'm going to specify bell and socket. And then I'm going to get even more specific and say the water's got to flow out of the bell into the other pipe. So you minimize the buildup of solids. Water flow into the bell to minimize the solids buildup on that transition. Okay? So you're flowing through it where you have rounded surfaces rather than hard, sharp surfaces. Use a chalk line along the length of the pipe so that you're drilling the holes in the same orientation, okay? In the same orientation. By Texas rule, the orifice is supposed to be facing down. Notice when I take a breath there. Maybe I agree, maybe I don't agree, okay? I was trained to put them up, okay? And here was the reasoning at that time. The reasoning at that time was the solids are going to be on the bottom, okay? So if your holes were up, then hopefully it would keep running longer, okay? Now, I'm going to say nowadays it depends on what your media is, okay? I had an excellent supper last night with Wendell. Wendell, are you in here? And he told me about the LPDs that he does. He uses the chambers. He straps the pipe inside the chambers. He has an 18-inch wide model that he uses. And he has the orifice going up because that splashes the water around. And I said, absolutely, okay? If you've got a chamber, you really don't want that orifice facing down because you're just going to blast out a hole there, okay? If you've got gravel media, I really don't care, okay? So you've got to go, you know what the rules are, okay? Understand the spirit of the rules and understand sometimes we beg for forgiveness when we don't follow them, okay? Use a sharp drill bit and, of course, the correct size, okay? A 7/16 is not the same as a 5/32. Okay, you get a completely different flow rate. And yeah, I had that happen to me, okay? I got the contractor to replace all that pipe, okay? Remove any burrs, but don't drill the whole way through it, okay? And that can happen. It could happen really, really easy. Okay, orifice shields. I believe in them. I've installed many of these without orifice shields. I've installed a few with orifice shields. It adds to the cost, okay? But if you're in a situation where there might be a rock sitting right there on top of that orifice, it's not going to produce the same amount of water. So if you can put that shield on there, that helps spread the effluent out and helps minimize any kind of problems you may have. Okay, the excavation. The excavation for the LPDD is just as sensitive as a conventional system. If we go in there too wet, we'll smear the clay, and that's bad. If we go in there too dry, we may pull up a bunch of clods and clumps. Be just too hard to work. So there's an old saying that's actually written in the Tennessee Code. Do not dig unless it's dry enough to plow, okay? It's written in the Tennessee Code. And the problem with that is people of my generation, especially our children's generations, have never plowed a piece of ground. They have no idea what you're talking about, okay? And so it's not a very accurate moisture descriptor. But if we go in there and smear that clay, it'll fail just as fast as any other system out there, okay? And that's true with any excavation that we do relative to that infiltrative surface. Lateral placement, Texas rule says place the lateral on at least 6 inches of media, place geotextile fabric on top of the media, backfill with Class 1B, Class 2, Class 3 soil, okay? Pretty standard things that we do with probably all excavations. My examples that I gave in there assumed a full foot of media being gravel, okay? Clean gravel for what that's worth. Tennessee, that's a rare commodity. All our quarries ground rock with respect to our Department of Transportation and could care less about our septic system industry, okay? And so I'm sure that's kind of true here too. So to get clean rock is pretty tough. The next design issue, those turn-ups, okay? We've got to have access to that pipe. It will grow solids. And so we need to have access to it and either a couple of 45s or a sweep. One of the, I think it was in Ohio, I was consulting more or less, and they specifically said in the rules that everything had to be Schedule 40 something that forbade me from going to an electrical conduit place and getting a Schedule 40 piece of conduit with a long radius sweep on it, okay? That's what I'd go to ordinarily. You know, just go get a piece of Schedule 40 long radius angle, okay, as your sweep, and you've got this nice smooth transition. It's still Schedule 40, but that state wouldn't let them use it. So you can use 245s instead and get the same issue. You notice on the bottom picture there, they're just using 145, okay? But that pipe's going up at an angle and would require a larger meter box to get to. Okay, mistake made. Mistake made. You see the turn-ups, you see the little boxes we had to protect the laterals and everything, but we didn't backfill with rock. And so every time somebody walked and stepped on one of those little boxes, it pushed it down in the soil. So we've got to bed those, okay? The boxes need a solid foundation or they will settle and or sink under yard traffic. Lesson learned on my part. So we've got to backfill those with rock too. Threaded end cap, you see the picture, okay, for pressure measurements and for clean out. The pressure's so low, you don't have to wrap them necessarily with Teflon tape, but you really do want to because it'll make it a lot easier to take off 5 years from now. If you like using these indexing valves, and I kind of do, there's a bunch of them upstairs. Remember, they freeze, but also remember you got to put them at the higher elevation because they have to drain in order to work. If they don't drain empty of water, they won't work. And so, got to remember the freezing situation, insulate the pit and the cover itself. Additional access notes, okay? You guys are so close to surviving this. 10 more minutes. They probably won't last that long, okay? Enough room in the riser to manually operate the floats. Don't violate the confined space entry rules, okay? I got these big old long arms, okay? I can get down there, I can lay down on the ground, stick my shoulder off in there. But if my nose, my face is over that riser, I have violated the confined space entry rule, okay? Pure and simple. And so we need enough room in there that we can lower a rake down in there and lift a float and operate that system manually, okay? I'll love to reach in there and pull that alarm float up just to make sure it'll work. Pull the lower float up, just to see if everything's making connections and stuff when I have a low tank. Backfill by hand to avoid damage. A little rock can do a lot of damage to a piece of plastic. You know that. Okay, so be careful on the backfill. Place components in the center and reachable. So what I'm saying there, if you've got this riser, try to have the component that you'll be working on kind of in the middle. Okay. In Tennessee, and I bet it's true in Texas too, if you put any box in the ground and you have a lid on it and you pull that lid off of it during the summertime, there'll be a black wood in there. Is that true here? Or snake, yeah. I've gotten a few of those, okay? So maybe we've got our valves not in this nice small manifold package that I showed you earlier. Early on in the development of LPP and LPDD systems, we had the valves on the individual laterals, okay? That's the case here, and so we needed access down to it to adjust the pressure. And so you see where we used a 4-inch diameter pipe as a casing to keep the soil away from that valve that's down there. And then we had a pair of tongs, I guess you would say, on the end of a piece of rod that we could adjust that turn on that without having to get down in there. Bed the pipe beneath the frost depth. Okay, yeah, this is the main line. And that place where that main line crosses that open excavation between the tank and the soil wall, that's a weak spot, okay? So we need to reinforce that. That's a weak spot. Thrust blocking, not a huge issue for us because typically we're keeping that velocity inside that pipe less than 5 feet per second. But when that pump kicks on or when a valve opens and suddenly we got flow and it goes down and hits a 90 degree, it's going to try to take that pipe on down with it, okay? My wife and I have one of these front-loading washing machines, okay? I wouldn't wish that on anybody else, all right? But it kicks its valve on very often, and all the pipes in my house go boing, 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 and I'm just waiting for one of those pipes to come apart. And so we don't want that to happen out in the field either. The process we refer to as water hammer. Upon startup, it's a great day. We've got this system built. Fill the tank up with clean water. Trust me on this one, okay? You don't want it full of septic tank effluent before you start trying out your stuff, okay? Trust me on this one, and take the end caps off the end of all your laterals so you can flush the PVC filings. And you've got a pipe, it's laying on the soil, you're putting it together, you're going to get soil in there, you're going to get gravel in there. So with clean water, take the end caps off, flush all your lines out, okay? It'll make the system work so much better. Then get your standpipe out, okay? So we've got a good picture of George Loomis there. He's got his finger on the elevation that he's shooting for. But the comment I want to make right here is that elevation is the static head pressure, okay, at that location. That's not the same as the squirt height, okay? The squirt height should be lower than your design elevation. So if you have access to the orifice and you're seeing the squirt of water coming up, that's not the same number we're looking at. We're looking at the static elevation inside that standpipe as being the pressure we're looking for. Tools to clean out laterals, plumber's pipe brush and electrician snake. Pressure, we can use a jetter type system that can backflush the water as we go. Be careful with these. We don't necessarily want to get the biggest, baddest pressure washer out there that we can't afford. Okay, you'll tear the system up too, but use caution with it. Okay, and as a way of finishing this up, you can see where one lateral at a time, we can take that end cap off and flush and bring that water up. Okay, and it gets a little more gruesome as we go. Okay, so that's pretty nasty looking. Hopefully by the time it's done, you can't see it very well on the slide, but hopefully that water starts to clean up a little bit. Okay? So question though, this is a good question. It really looks lovely right there. Okay? Do we really want that flushed material in the consumer's yard? And we've kind of been content doing that for a lot of years now. A lot of times it just goes down in this open void right here. But we might think about being creative about how we can move that liquid around back to the septic tank. Because I think we truly want to avoid this. I think we really don't want that out in somebody's yard, okay? Fluffy rolls around in it and then goes back in the house with it when Fluffy's fur. Probably not a good way to have them have good feelings about us when they go to write a check for our services, okay? But if you do have this, a recognized best management practice is to sprinkle some lime over that to disinfect it, okay? And it's not all bad for the yard either. Okay, Texas rule, start, stop switch or timer must be included in the system to control the dosing pump. An audible and visible high water alarm on an electric circuit separated from the pump must be provided. We've talked about that already. But beyond the alarm, I want to recommend an elapsed time meter so we can see how long the pump has been working. So when we come back every 6 months to look at it, we'll know how many hours are on the pump. An event counter, so we'll know how many times the pump kicked on and off, okay? And of course, what we have to have is a timer, okay? So we have to have something. If we're doing, of course, time dosing, we have to have something to tell the pump when to turn on and off. Okay, I just raised the price of your control panel $200. Okay, so you can fuss at me, but this is good information. Here we just raised the control panel price up $400, but you don't need this, okay, unless you're doing a school or a camp or a larger flow, okay? And schools and churches are two of the toughest systems that we all can work with, I must admit, okay? Does my control panel look scorched? It looks scorched because we have gases coming in from the septic system, and we need to look at using grommets and such to minimize that effect, okay? And this is the one I've always got to show. Don't do your electrical connections like this. If you look real close, you can see where they went from Romex, it's on this one. They went from Romex, which is square cable, to round cable, and used electric tape and just left it in the riser. It's just plain dumb, okay? Could electrocute the owner, could electrocute yourself, and congratulations, 2 hours, good job, folks. Give yourself a hand. All right. Come talk to me if you got questions.